Hi, this video is an introduction to proofs in math. In math, we often must prove that a statement is true. That means we must prove that it's true all the time. Usually we do this by starting with something else that's known to be true, and then we mathematically lead step by step to the statement that needs to be proven. Now, when I say to prove a statement is true all the time, underscore all the time. The fact that something is true some of the time or most of the time or even almost all the time is not enough. What follows is that you cannot prove a statement simply by giving examples of when it's true. Examples are good illustrations, but they only show the statement is true for those examples, not all the time. They are not proof. Consider this. Prove that all even positive integers are composite. The statement to be proven is all even positive integers are composite. By the way, a composite number is a number that's not prime. If this statement's going to be true, it must be true all the time for all even integers. Well, it's true almost all the time. 4, 6, 8, 10, etc. all the way to infinity. They're all composite. If you randomly select one even positive integer every second, chances are you go for years and years and they're all composite. But you and I both know the statement is not true because the number 2 is even and it's a prime. Now you see, to prove something is true, you must show that it's true all the time, not just almost all the time. All means all. That's why you can't prove just by showing examples. That's lesson number 1. Lesson number 2 is one example where it's false is enough to show the statement is false. We call that a counterexample. Here's how it works. If something is supposed to be true, it must be true all the time. Therefore, if something is supposed to be false, that means it's not quote-unquote true all the time, then it only needs to be false just one time. I sometimes tell this story in class. Mom would often say that she loves all her children equally. What would make that statement false? Does she have to love all her children unequally? No. It only takes one favorite child. To prove something is false, to disprove something, all we need is one counterexample. Now, on to another topic. When you make a statement to be proven, it must be well-defined. A well-defined statement is something that we can set out to either prove or disprove it. This does not depend on whether we're capable of proving or disproving the statement. A statement is well-defined as long as it's clear enough what it is that must be proven or disproven. Well-defined also doesn't mean true. It can be false. If it's clear enough to be disproven, it's still well-defined. Back to our saying that to prove a statement means must prove it's true all the time. Last time I underscored all the time. Well, this time I need to put an asterisk on it. The asterisk is the statement itself must be clear as to what all the time means. Here's a statement that's not well defined, or as we say, ill-defined. Prove that 2x is greater than or equal to x for all x. At first, it looks like a good math question. It looks like we can compute 2x and x and maybe do some algebra and either prove that this is true or find a counterexample. But here's the problem. What kind of x are we looking at? See, this statement is not well defined. It's unclear what kind of x we're talking about. Natural numbers? Real numbers? Complex numbers? Matter of fact, if x is a non-real complex number, then the whole comparison greater than or equal doesn't even make sense. The greater than or equal relationship is not defined in the universe of complex numbers. To be well defined, the statement itself must be clear where it's applicable. The statement must be clear as to its domain. Let's fix it and make it well defined. Something like this. Prove that 2x greater than or equal to x for all x in R, the set of real numbers. Now it's a well-defined statement. It's clear what it is that we need to either prove or disprove. Either we prove this, or we find a real number x where the inequality doesn't work. Well, is this a true statement? Our gut feeling at first may be that it's true. If we take a number x and we double it, it gets bigger. But that's not actually the case all the time. Here's a counterexample. When x is equal to -1, then 2x is equal to -2, and that's less than x, which is -1. This illustrates a problem with relying on intuition or gut feeling. When we're first starting out doing proofs, a lot of our intuition or gut feeling will be based on very simple and nice things. Things that behave nicely. For numbers, our intuition tends toward positive integers only. In geometry, we tend toward figures that look nicely proportional, more or less with equal sides. In calculus and differential equations, our gut feeling is mostly based on continuous functions with continuous derivatives. They got nice and smooth graphs. In linear algebra, we may tend toward vectors that are on the xy plane and that are pointing in different directions. In graph theory, we tend to think of planar graphs that are connected. It takes practice to remember to think about things that are less nice. Negative numbers, irrational numbers, non-algebraic numbers. Functions are not continuous, they have breaks or holes. Or they have sharp edges, meaning the first derivative is not continuous. Vectors that stick out of the xy plane. Vectors in n dimensions. Vectors that may be 0 or linearly dependent. Matrices that are singular. Matrices are not square and therefore don't have determinants. In graph theory, non-planar graphs, graphs with extraneous things like loops and double edges, graphs that are disconnected. This more mature form of math intuition comes from practice. You may get some practice by watching other people do proofs. These other people may be your professor, the textbook, your classmates, or someone you saw on YouTube. But it will come mostly from you doing your own proofs and finding your own counterexamples. And like most things, the more you fail at the beginning, the more that builds up your intuition, and eventually you make less mistakes later on. Now let me do an example of a proof. Prove that given x in R, meaning x is a real number, then 2x is greater than x if and only if x greater than 0. First, I need to explain the words if and only if. It means the logic flows both ways. If I have 2x greater than x, then it follows that x is greater than 0. But also the other way around, meaning the converse. If I have x greater than 0, then it follows that 2x is greater than x. Once I have the statement and the converse true, it follows the inverse is also true. If I don't have 2x greater than x, then I don't have x greater than 0. As a result, there are two main ways of proving an if and only if statement. Method 1 is to prove the statement and its converse. Prove that 2x greater than x leads to x greater than 0. And then prove that x greater than 0 leads to 2x greater than x. Method 2 is to prove the statement and its inverse. First, prove 2x greater than x leads to x greater than 0. Then prove that if 2x is not greater than x, meaning 2x is less than or equal to x, leads to x not greater than 0, meaning x is less than or equal to 0. And then, of course, there are many other ways as well. For example, you can directly prove an if and only if statement by going from the starting point, 2x greater than x, and using only math steps that go both ways, lead yourself to the finishing line, x is greater than 0. I would do method 1. You may want to hit pause and try it yourself before moving on. Right, let's prove this. But before I prove, I want to mention that this phrase here, if and only if, is often abbreviated as if with a double F. So when you see IFF, you know it stands for if and only if. It can also be written in symbolic form as a double arrow pointing both ways. I'm going to approach this with method number 1 to prove the statement and then prove its converse. So first I'm going to prove the statement, meaning it's going this way. Before I prove anything, I strategize. A good strategy, especially when you're first starting out, is whatever it is you need to prove, you go to the definition of it or some basic properties of it. In this case, what we're proving, either direction, is an inequality, the greater than inequality. So we want to go back to the definition of what it means for something to be greater than something else. What does it mean for A to be greater than B? The definition is that A is to the right of B on the number line. Well, this doesn't help. If the definition doesn't quite help, you go to some other basic properties of it, meaning what else is there that I know about the greater than relationship? What else does it mean? I go to one of the basic properties. I call it basic because it's something that you learn when you first learn to subtract numbers. And that is that when you first learn to subtract, you always take a big number, subtract the small number, because that way you get an answer that's positive. And back when we first learned to subtract things, we only knew positive numbers. The basic property of A being greater than B is that A minus B is a positive number, meaning it's greater than 0. You can think of this as subtracting B both sides, but I like to think of it as a basic property of being greater than. When you're greater than something, then you subtract that thing, the answer is positive. This is more promising because I can manipulate a difference, a subtraction using algebra. It's really hard to manipulate positions on a number line. It's still doable, but it's just hard. So I'm going to go with this approach. So I start out with 2x greater than x, and I use this basic property and say that that means 2x minus x is greater than 0. Like I said, you can also think of it as subtracting x both sides. Well, 2x minus x is just x greater than 0. Oh, there we go. I start out with 2x greater than x, and I end up with x greater than 0. So I have successfully proven the statement going this way. Now I'm going to prove the converse. I'm going to prove the statement going backward like this. I'm going to start out with x greater than 0. Well, now that I have done it in one direction, it gives me a hint on how to do it the other direction. Going this way, I was using a property that looks like I'm subtracting x both sides. So if I'm going to go that way, I'm going to do the opposite of it, which is to add x both sides. So I'm going to add x both sides. And I arrive at 2x greater than x. I have now proven both directions. going from this inequality to that inequality and going back. That means I'm done. And traditionally, when you're done proving something, a lot of people put down this acronym QED, which is short for a Latin phrase that means that thing that must be proven. I have arrived at that thing that must be proven, so I'm done. Let me summarize with some advice. 1. Always strategize first. Work out the general strategy before writing down the actual proof. Number 2, the strategizing should be far enough along so you have at least the outline of the proof organized in your head before you start committing it to paper. If the question asks to prove something, start from some basic properties of the thing to be proven and move from there. Or start from the definition and move from there. If the question asks to disprove something, try finding a counterexample. Usually you find them in things that are not nice. Nice things behave nicely and they don't tend to contradict what it is you're trying to disprove. All right, hope that helps. Any questions? Ask in the comments. Subscribe for more contents. Thanks for watching. Bye.